Thanks very much, Chris. Well, and thank you to all the organizers, all the other organizers also for organizing this. I guess this is the obvious start I have to make. So this talk will indeed be about what METIS will be able to do on the torus, and it will be a bit more on METIS than on the torus because Bernhard had to didn't have time to prepare a poster about METIS itself, and we have plenty of other talks about the torus already. So let me show you what we can do. Yes, so METIS is a collaboration of many different institutes, actually all across the world now, including European institutes, but also Michigan and even Asia A in Taiwan. So we also know how to deal with lots of time zones. So for those of you who are not regularly in ELT instrumentation, let me just put this briefly in perspective. So METIS is really a huge instrument compared to something like Visier or even METI or METIS that you might have seen in the past. So the instrument itself has about 20 tons. And if you would put it on the ELT, it would still, of course, be small, but actually if you would put it on or if you compare it to a VLT, this is a VLT compared to the ELT now, you see that the VLT is really small compared to the ELT. So here the 8-meter telescope is on the NASMET platform of the ELT. So you can see the METIS is almost comparable, like a third or something in size, in width almost as the VLT. So it's really a huge instrument. And of course, also a huge effort to put this all together. This is how it will look like in the schematic drawing. This is from the optical FDR that happened last year. So the optics is now more or less frozen, and METIS has a number of different modes. It will be, as you might know, the only, at the moment at least, it's the only funded thermal infrared imager for the ELTs. We hope, of course, to get MICHI. Chris might say more about this at some point, and possibly even more, but at the moment, METIS is the only one that is kind of guaranteed and in the process of being made. So we tried to put everything in METIS that we can, so that it covers all aspects of thermal infrared astronomy. That means you get L and M band imaging and also L and M band long slit spectroscopy, the same in the N band imaging and long slit spectroscopy. And in addition, we have a high resolution integral field unit in the L and M band that gives you, at a resolution of 100,000 spectral resolution or 3 kilometers per second, very small field, 1 by half an arc second, gives you parts about 50 microns, 50 nanometers at a time for the L and M band. There's a different mode where you can expand the wavelength range a little bit on the cost of spatial coverage even more. We have a single conjugate adaptive optics system. So you need to have one bright central star, K-band magnitude of 11 or better, ideally, to guide the telescope and to do the adaptive optics correction. And we have a number of other units that are there for the beamforming, like the Born calibration unit that you can see on top, and the whole common 4 optics here that does the derotation and has various other beamforming capabilities, mostly for high contrast imaging. You heard a bit of this from Olivier the other day. So this is just to remind you of the spectral transmission that we see through the atmosphere. In these bands, of course, very, very well known to many people. So L band, M band, N band here. We have a resolution of 23 milliarc seconds at 3 microns. So we can compare this, if you want, to current instruments where you get something like 60, 70 milliarc seconds, of course, factor 4 to 5 for the VLT. But you can also compare it to the VLTI, where you get something like 3 milliarc seconds. So it's really in between. And just to repeat here, so we get diffraction limited imaging, long slit spectroscopy, and high resolution IFU in the L and M band, and we get diffraction limited imaging and a long slit spectroscopy mode for the N band. Now, moving on to what this all means for the AGN. This is, as we saw in the very beginning in the introductory talk by Christina, this is kind of the picture that we have at the moment for the AGN torus. So there is a disk that is probably thick, that is the one that we see with the VLTI studies, for example. We have probably some inner sublimation region where a lot of near-infrared emission is coming from, which might also be responsible for the actual dichotomy of the type 1, type 2 phenomenology. And we have lots of emission in the polar cone. And then this can be expanded also to other wavelength branches. So is the thing actually solved? Do we now know what the AGN looks like? What are still the open questions? Well, as we heard in a very nice demonstration from the difference in interpretation between Violetta and Pierre, there is still discussions about what the actual size and structure of the AGN heater dust is, and mind you that we have only done this in so much detail for really 2 sources, for 1068 and the Circinus galaxy. So there's still a lot to be done there. Also, this polar dust, as Christina pointed out, we really don't know what it is. Is it an outflow, or is it just illuminated dust in the galaxy that is just sitting there? And also, this was also a question that has come up: is it reprocessed dust? So has it been going through the center, and is it lifted up, or is it just sitting there? And then, of course, the million-dollar question is: what does that actually mean for AGN feedback? Is there any connection between this polar dust and the galaxy, and what does that do to the galaxy? Also, we'd like to know the kinematics of all of this. We hope to do this with the L&M band high-resolution IFU. And the biggest question for me, at least, is why actually are some galaxies active and others not? And that's where the time zones, of course, come in. But we hope to come closer there with METIS at least. Now, if you look at what can be done, we have seen this before for a single image, for single telescopes, single dishes like Visier. You can hardly or just barely start to resolve it. With MIRI, also what Christina pointed out to, we will hopefully see, we have about the same resolution as Visier, but we hopefully see the more extended colder dust, of course, mostly because we have also filters that go into longer wavelengths. And then on the other hand, we have these fantastic high resolution studies from VLTI, as you saw just before. And actually doing this on a couple more sources, as we did from METIS, still you see that most of these sources are actually polar elongated. And this is not just nice to have, but this might actually have some real physical meaning. And this is one of the most interesting results, I think, that actually came out from all the VLTI studies. So this is I would say, almost a proposal or an idea put out by James Leftley and collaborators. And he speculated really on this relation, that the amount of polar dust, this is more or less what you see here on the y-axis, the prominence of polar dust, has a relation with the Eddington ratio of the AGN. And he kind of demonstrates this for a number of sources that are seen here. And if that's true, that would mean that the polar dust is really lifted up by radiation pressure, likely, because that is what is essentially changing as you gear up the Eddington ratio. So that is a very interesting result to follow up on. And for that, you really need more of these polar elongated AGNs and study them in more detail. And for these, I think METIS will be really the instrument to look at, of course, because if you look at some of the fainter AGNs, so not NGC 1068 or Circinus, as we've seen before, which can be studied with a lot of detail already with single telescopes and with even more detail with VLTI. If you look at some of the more typical AGNs that have a total flux of about a Jansky or less, then often with VLTI, we're actually lacking the baselines just between 40 meters, where most of the flux is missing. So you can see, for example, for NGC 4151 very clearly, if you look with VLTI, the highest visibilities that you measure are of order 40%. So 60% of what's happening between the point source that is unresolved in a single telescope and the 40% visibility that you see with VLTI is just unknown. And this is really where METIS will come in and hopefully see lots of structure in the polar outflows. We can simulate this now, of course, taking whatever models you want to look at. This is with a rather complicated model, a hydrodynamical model ran through a radiative transfer process and then ran through our own METIS instrument simulator by Violetta, actually, a couple of years ago already. And this is what you can see here again, as a function of Eddington ratio, we can see some quite drastic changes in morphology that should be observable. But also spectroscopy can be very interesting with METIS. There is quite a number of lines, so to say, on the menu, I would say, from 3 microns up to 12 microns, so all the way from L, M, and N bands. We have recombination lines, we have coronal lines, we have molecular transitions, hopefully, although we haven't seen them so much in the very centers so far. And but here's again some spectra where you can see what is typically observed in AGN. So not too many lines, but we can see bracket alpha and silicon 9. Of course, with higher sensitivity in METIS, we hope to see more. And in the end band, we have, of course, the silicate feature, but then also a number of lines that can be studied. So neon 2, of course, in the end band, sulfur 4, argon 3, and the dust feature itself. And this is actually to answer one of the questions that came out before. So what can you actually do with the dust? I think that was actually Ryan's question. So one of the studies that we want to do is really test these 2 scenarios. Is the dust coming into the midplane and then
you have 1 minute.
Thank you. Then partly sublimated and being driven out again, or is it just coming in and evaporates and goes away, and the dust that we see is in the galaxy? These two scenarios should be distinguishable by looking at the spectra. All right, I will skip this here for the hidden broadline regions, just to say that METIS will be quite complementary and also actually not so bad in sensitivity as you might think from the near-infrared, from the mid-infrared, because we're looking at bracket alpha compared to bracket gamma, which is quite a bit brighter. Quickly here, the number of observable sources should be on the order of about 300 at least, if we go to the maximum performance of our AO. And if we can accept the slightly degraded AO, mind you, this is for 3.7 micron, and 10 micron, the AO is even better, then we can probably go close to 1,000 sources. So we will not really be limited by the number of sources, but more by telescope time. So we have to think a little bit about which sources we want to observe. And for that, we will use the METIS simulator, which this is just very recent results or very recent development. We can use this to, for example, look exactly at this science case. So study here, if we do this, if we place the slit along the direction of the outflow, we can see nicely this extended emission and then study differences in dust properties. This brings me to the summary. Mid-infrared interferometry and imaging have resolved 30 nearby AGNs, and we see this new model coming up that polar emission is very important. With METIS, we will be able to study hundreds of AGNs and in particular be sensitive for this polar emission. METIS itself is going to go through final design review this year, and first light is expected 2028. The simulator, however, is expected to be released next week. So if you want to start playing with METIS, you can start this now. Thank you.